Hey folks, welcome back. We've talked about a bunch of theory around hypothesis tests. Let's actually go through the steps and you will see that there's really nothing new here that we've been looking at. We're just going to add one little bit of new thing here, which is called the level of significance and the critical value associated with that. But we've talked about that. We're just going to formalize that. So let's take a look at the steps of the hypothesis test. And there's 5 main steps here. We're going to look at something called the classical approach and then the p-value approach. The thing about the p-value approach is that that's often the approach that students have trouble with, which is kind of funny because that's actually the way that we solved the problems all through units N and units E. We were actually doing the p-value approach there. But let's take a look at this problem, and we're going to go back to the cigarette example, and we're going to use something called the classical approach for hypothesis testing. So, to get back to where we were on this one, manufacturer of a certain brand of cigarettes claims, telling us that this is a hypothesis test, that the cigarette contains on average, so that's a mu, no more than 1.6 milligrams of nicotine. Hypothesized mu. An independent testing agency examines a sample of 144, little n, yielding a sample mean, an x bar of 1.7, and a standard deviation, 0.5, is our S. Does the sample support the claim? The null hypothesis, then, is the standard. It's the status quo. It's what needs to be met here. So we're not going to slap them with a fine unless we have enough evidence to disprove the null hypothesis. And so the null hypothesis is that mu is less than or equal to 1.6, that they are meeting the standard of no more than 1.6 milligrams of nicotine. At this particular point, we haven't taken the sample, so don't even look at the 1.7, the 0.5, and so on like that. We're just looking at the hypotheses. The alternative is that mu is greater than 1.6, pardon me. So there's your HO and your HA. That's step 1. Step 2, identify the appropriate test statistic to use for this particular problem. So this is where we're going to go back to the formula sheets that we looked at before. All right, so let's go through this again. Is the population normal? So this part right up here. No, it doesn't say anything of that in the problem. Is n at least 30? The answer to that is yes. N was 144, so the central limit theorem kicks in. Is sigma known? And the answer to that is no. That means that we're going to be using a t-distribution. Is big N known? Doesn't say anything about that, so we're going to be using formula number 3. Just going to get rid of all those. Okay. Formula number 3 down here. If this were confidence intervals, we'd be on the left-hand side, but we're talking about hypothesis tests, so we're on the right-hand side. So here is formula number 3 from the flowchart. And you're going to have that flowchart with you on an exam. So this is the formula that we use here. Okay, step number 3 is new for you, but we've actually seen how to do this before in the earlier units. Find the value in the t or z distribution, in our particular case it's going to be t, that has alpha percent in the tail. This is called the critical value. If alpha is not given, then we're going to assume an alpha of 5%. So there's nothing in the problem that said what alpha was, so we're going to assume an alpha of 5%. This area may be in the upper tail, the lower tail, or split between the two, depending on the form of the hypothesis. We're going to actually talk about that afterwards. Basically what you do, I'm going to show you how, the quick and dirty way of doing this. You look at the sign of the alternative hypothesis and it acts like an arrow. It points, in this case, to the upper end of the distribution. So that's where you put your alpha. So let's actually draw this out here. So here's a t distribution. It's got 143 degrees of freedom, which is n minus 1. Your n was 144. And so we want to find this particular value here that has alpha percent. In our particular case, is going to be 5% in the upper tail. And that's going to be our critical value. So the way that we write it is this way. We're looking at a t of alpha and n minus 1 degrees of freedom. So t of 0.05 and 143 degrees of freedom. So we're going to go back to a t table to find that. So 143 degrees of freedom is right here. So we're going to go to the Z line, and we go under the 5% column. And so at the bottom of the 5% column is 1.645. So 1.645 then is the value that corresponds to 5% in the upper tail. Okay, so it's 1.645. In fact, I've got that written right here. So that's what we call our critical value. Our decision rule is this, that when we figure out our T star formula, if the T star value turns out to be greater than 1.645, then it means it falls in this upper tail here, so it's in the critical region or the rejection region. And so we would reject HO in favor of HA. So this is what we call our decision rule. If the computed T star is greater than 1.645, which is our critical value, then we reject HO in favor of HA. This is best shown in the following picture. I think I actually drew the picture up there. So right up here. So if we end up with a T star in here, this area, then it's in the rejection zone. Step number 4 is to actually take the sample and stick it into the formula. So we've got our 1.7, we've got our 0.5, we've got our 144. This is, of course, our hypothesized mu value, and we end up with 2.4. 2.4 is greater than 1.645, so it's in the rejection zone. So our conclusion then is that it falls in the rejection zone. So I've shown that in as the picture up here. And so we reject HO in favor of HA. So 2.4 is greater than 1.645, therefore reject HO in favor of HA. The manufacturer's claim is probably incorrect. There is a chance that we're making a type 1 error. Let's take a look at the decision rule. And there's various types of tests that we can have. So this one that we just looked at here is what we call a one-tailed test. And the way that this works here is, let's just draw a little distribution here, and this can be either a Z or a T, right? In our particular case, of course, it was a T. Sigma is known, then you'd be using a Z distribution. And what you do is you look at the sign of HA, and that points like an arrow to the upper tail. And so what you do is you put the whole alpha in the upper tail. And so what we have here then is that if Z star, or computed Z, or that could be a T, right, T star, is greater than a Z alpha or a T alpha, then we would reject HO. Why? Well, if you ended up with a really low Z star or T star, so if you ended up with something down here, well, that's not a problem. That just supports the null hypothesis. The null hypothesis is satisfied with any x bar which is less than 1.6. It's only if it's significantly higher than 1.6 that we would reject HO in favor of HA. Think back to our nicotine example. If it turned out that the average amount of nicotine was, say, 1.2, and you're allowed up to 1.6 milligrams of nicotine, government's not going to mind on that one. They're going to say, yeah, you're meeting the standard. You're way below what you need to be, but you're meeting the standard. All right, this is the opposite kind of thing over here, and that's where you've got mu is greater than or equal to 10, and the alternative is that mu is less than 10. So in that particular case, what you do is you take a look at the sign of the alternative hypothesis. So this would be a Z or it could be a T. And you take the alpha and put it in the lower tail. So you put the whole alpha down here. So it's only if you ended up with a very low Z or T value, it would be a negative value, right, that you would reject HO. So here's an example down here. If your Z star is less than minus 1.645, which is the Z value associated with 5%, we would reject HO. In a two-tailed test, what you do is you say your HO is just simply that mu is equal to 120. And so either a very high X bar or a very low X bar would cause you to reject HO. So what we do in that particular case then is we take our alpha and we split it in half. You still want in total an alpha percent, let's say a 5% level of significance. But what you do then is you take your alpha and you split it in half. So you put alpha over 2 here. If you got a really high value, you put alpha over 2 here for a really low value. And if it falls in either of those two areas, then we would say that it's significantly different from the 120. So down here, what we do is we say if your Z star, or again, that could be a T, right, is less than a minus Z alpha over 2, or if it's greater than a positive Z alpha over 2, then it would be way out in the tails there. You would reject HO. So in this particular case, then, we would be using 1.96, which is the alpha associated with 2.5% in the tail. So here's the thing to remember. The sign of HA tells you which side of the distribution contains the critical region. So it's like an arrow that either points up or down, or if it's not equal to, then you split the alpha. Now, the alternate way of doing it is what we call the p-value approach. And in the p-value approach, what we do is we say, instead of finding a critical value and then comparing the Z star or the T star to that critical value, what we do is we find the T star or the Z star, and we find the area associated with it, and we call that area the critical value, the p-value. And if the p-value is less than alpha, then we reject HO. So let's take a look at how that works down here. Let's take a look at our nicotine example again. So what we do in this particular case then is we take a look this was a t, or it could be a z, right? A t or a z. In this particular case, we get a t star value or a z star value. I guess I'm using z's here, so let's call that a z star. Okay, and you take a look at the sign of the alternative hypothesis, and that says wherever the z star lands, you calculate the area going up. And we call that the p-value, the probability value. Here's the decision rule, is that if the p-value is less than alpha, you reject HO. So if you have an alpha of, say, 5%, if this area turns out to be less than 5%, then it means that it's way out in the tail, and you would reject HO. When we are dealing with this kind of problem here, then what you end up with then is a t star, and we would calculate the p-value this way because that's what this is showing us. It's an arrow that goes to the left. One thing that's really important to note here, folks, and that is, well, what happens if you ended up, by the way, that would be a negative t star or a negative z star. What happens if you end up with a positive one in this particular case? You would still calculate the area going down. So you would calculate that whole area there, because that's what the sign says to do. So you can actually end up with a p-value very high, like 90%. That just really supports the null hypothesis. It's only a really small p-value that causes you to reject the null hypothesis. Same over here. If you ended up with, say, a negative t star, then the sign still says to go up to calculate the p-value that way. So it could be really high, like 99%, and that just supports the null hypothesis. The decision rule is always, always in a p-value approach, if the p-value is less than alpha, reject HO. In fact, that's kind of like the stats mantra. You need to remember that. Stick that on your fridge. And here's what I always tell students. If 20 years from now I meet you on the street and you've got your children in tow, and I'm an old man and I come up to you, I'm going to say, "What's the stats mantra?" And you should be able to tell me, if the p-value is less than alpha, reject HO. And if you don't, I'm going to embarrass you in front of your kids. Okay? It's that important. It really is. Now, in a two-tailed test, what we do is we either a very high or a very low t star value or z star value would cause us to reject HO. So suppose you end up with a t star here. If it's a positive value, so you're in the upper tail, you calculate the area that way. If it is a negative value, you calculate the area that way. And then what you do is you multiply the area by 2. So 2 times the area is equal to the p-value. And so if 2 times that area is less than alpha, this whole thing is called the p-value, then you reject HO. So the p-value then, the area is doubled to get the p-value. Why does it work that way? Maybe if I superimpose the classical approach over the p-value approach, it'll make more sense. So let's put the two together. Okay, so this is a z or a t. In a classical approach, what we do is we find an area associated with alpha. So this would be a Z alpha value, or it could be a T alpha value. And then what we do is we find a T value, a Z star or a T star value, and it's actually associated with a P value. In the classical approach, what we are doing is we're comparing these two guys. So we are comparing a computed Z star or T star, like in the nicotine example, to a critical Z or a critical T. In the p-value approach, we compare areas. So each Z value is associated with an area. The critical Z in the red is associated with alpha. The computed Z in the green is related to the p-value. In the classical approach, you compare the Z values, or T values, and in the p-value approach, you compare the equivalent areas. Now, the thing to note about a two-tailed test is, remember that what we did in a two-tailed test is we split that area in half. And so we actually had alpha over 2 here. So what you could do is you could find that area and compare it to alpha over 2. But what statisticians do is they multiply both of those by 2. And so the area is multiplied by 2. This green area is multiplied by 2. And then you can compare it to the original alpha. And so you still have the same decision rule. If your p-value is less than alpha, reject HO. You just need to remember that in a two-sided test, you find the area and multiply it by 2 to get the p-value. And then you compare it to alpha, not alpha over 2. So hopefully that helps you understand how we do this. In the next thing we're going to do here is to work through this using a p-value approach. And then we're going to work through some problems here.